Hello and welcome to Empowered Learning. This particular video will be to do several examples on simplifying trigonometric expressions by either doing multiplication and or factoring to do so. I'm going to have several examples here, so if you need to pause at any time to take a break or whatnot, please feel free to do so. So let's start with our first example. So we want to simplify this particular expression. And so when we multiply this, we're thinking after we multiply it, what kind of identities can we use? So looking here, let's just go ahead and multiply this together. So if we do this, we see that this is like A plus B times A minus B. And we know that when we multiply that, if we FOIL that out, it ends up being A squared minus B squared. So all this would end up just being 1 minus secant squared of alpha. Okay. Now, if we look at this, we'll say, all right, well, this looks kind of familiar. This may be one of the Pythagorean or reciprocal identities. So to see which one it is, we can just do sine squared plus cosine squared equals 1. And try to get secant squared somewhere. So here, what I'm going to do is divide both sides of my identity here by cosine squared. And if we do that, we get tangent squared here plus 1 equals secant squared. And in this case, it would be secant squared alpha. So we'll just call this tan squared alpha plus 1 equals secant squared alpha. And so here we see that we can take secant squared and rewrite it as just tangent squared plus 1. Or what we could do is just figure out what 1 would look like. So it doesn't really matter how you want to do it. What I'm going to choose to do here is just rewrite secant squared directly as tangent squared alpha plus 1. So here that would be tangent squared alpha plus 1. And of course, if we distribute the negative across there, we'll see that we have 1 minus tan squared of alpha minus 1. And that cancels to 0. And we end up having minus tangent squared of alpha as an answer. Okay. Now we could also write it this way as well if we wanted to, because we know tangent is an odd type of function. Okay. All right, so let's move on to the next example. So for this example, we want to simplify the following expression by first writing all functions in terms of sine alpha and cosine alpha. Okay. So in doing this one, just going to start off copying what we have. And then for cotangent, we know that cotangent is the reciprocal of tangent. So that would be cosine of alpha divided by sine of alpha. And then all that multiplied by sine of alpha. So you see here in this last term, we have the sine alphas reducing to 1. And now what we have left is just 1 plus cosine alpha times 1 minus cosine alpha. So if we continue on, we know that this is like A plus B times A minus B. And we know that's equal to A squared minus B squared. So when we multiply all this, we just get 1 minus cosine squared of alpha. And of course, if you recognize this is a trigonometric identity, and this ends up being sine squared of alpha, because if we come here and say sine squared plus cosine squared equals 1, and then we subtract both sides by cosine squared, you see that we get 1 minus cosine squared, which is exactly what we have here, and therefore our answer is sine squared of alpha. Let's move on to the next example. So for this example, we're asked to simplify this particular expression. And so this time we notice that we're dealing with a bunch of reciprocal trig functions. But the good thing about this is that we recognize that we have a pattern going on here. If you notice, cosecant to the fourth of theta minus cotangent to the fourth of theta can be rewritten. This is the difference of two perfect squares. So in particular, we'll just say note that cosecant, and I'm going to write it this way for clarity, minus cotangent of theta, all that raised to the 4, could be rewritten this way. Cosecant squared of theta, all that squared, minus cotangent squared theta, all that squared. And so, of course, this looks like a squared minus b squared. And we know that is just going to be a minus b times a plus b. So in doing that, we can rewrite the numerator for this as being cosecant squared of theta minus cotangent squared theta times cosecant squared of theta plus cotangent squared theta. So when we go and rewrite all this, this is what's going to start us off and get us in the right direction. So here we just rewrite this as cosecant squared theta minus cotangent squared theta, and all that multiplied by cosecant squared theta plus cotangent squared theta. And then we just put cosecant squared theta plus cotangent squared theta in the denominator. And if you notice, we have two common factors in the numerator and denominator, so they reduce to 1. And now we just have cosecant theta minus cotangent theta. Okay, so now at this point, we're looking at this and we want to check out to see, all right, is there any identity going on here? And so what we can do, again, is to come over here and start with our sine squared plus cosine squared equals 1 and see if we can come up with either cosecant or cotangent. Well, to come up with, let's see, cosecant, what we can do is divide both sides of the equation by sine squared. So if we do that, then this is just 1. Cosine squared divided by sine squared is cotangent squared. And of course, 1 over sine squared is cosecant squared. So we see here that 1 plus cotangent squared theta equals cosecant squared theta. And if we subtract cotangent squared theta from both sides, I'll go ahead and move this up, then this ends up being 1 equals cosecant theta minus cotangent squared theta, which is exactly what this is. So this tells us that our result just ends up being 1. Okay, let's move to our next example. So for this example, we want to simplify this particular expression here. Since we have two fractions that have unlike denominators, we need to create a common denominator. And so the LCD for this least common denominator would be cotangent x times cosecant x. So for this first term, what we would need to do is multiply the numerator and denominator by cosecant x. And for the second term, we would need to multiply numerator and denominator by cotangent x. So we'll go ahead and do that now. So we have cosecant x divided by cotangent x. And to get the LCD, we need to have cosecant x here. So cosecant x is also in the numerator. And then minus cotangent x divided by cosecant x. And of course, we need cotangent in the denominator, so we also put it in the numerator. So once we're here, we go ahead and we multiply, and we see that we have cosecant squared x over cotangent x cosecant x, and then minus cotangent squared x over cosecant x cotangent x. Now we combine that together, and we have cosecant squared x minus cotangent squared x, and that just gives us that over cotangent squared x cosecant x. Now, if you remember from our previous problem, we found out that cosecant squared x minus cotangent squared x, that particular identity is equal to 1. So all of this in the numerator is just equal to 1. So now that we have that, we can go ahead and finish this up by noting that we can split this up as 1 over cotangent x times 1 over cosecant x. And of course, this is saying the reciprocal of cotangent is indeed just tangent. And I'll go ahead and write this here. And the reciprocal of cosecant is indeed sine. So our result here is that we end up having tangent x times sine x be the equivalent of saying this expression here. All right, so let's move on to our next example. So in this example, we see that what we are asked to do is simplify the trigonometric expressions by factoring. And so one thing that we're going to do to make this easier for ourselves so that we can see it the way that we're used to seeing it is we're going to write sine of theta. So I want to come here and say let sine of theta be equal to s. Okay. So if we do that, this turns into 5s squared plus 13s minus 6. And so now all we need to do from here is just general factoring. So I'm going to do factoring by trial and error method here. So if we do that, of course, since we have plus minus, then of course one of these is plus, one of these is minus. Our first term is 5s squared. And so since our leading coefficient here is a prime number, we can just write this as 5s and s. And of course, all the factors of 6 is that we can use here are either be 1 and 6, 2 and 3. So in this case, if we use 1 and 6 here, we'll see that, and I'll just put it there, 1 and 6, you'll see that when we do the FOIL method here, we will get 5s times 6, which is a negative 30, and 1 times s, which is a positive 1s. And of course, that's going to be too big. If we switch it around and make this 6 and make that 1, of course, then we have a situation where we have a minus 5s plus 6s, which doesn't give us a 13. So we need to use 2 and 3 here. So to make this work, we will need to use a 3 here and a 2 there. And of course, when we multiply this out, that's going to give us a negative 15s, and multiply this, that gives us a positive 2s, which gives us net result of negative 13s, which we see that we need a positive one, so we can just change the signs here to make this work. Okay. And of course, that would change, and now we're good. So this is just 5s minus 2, s plus 3. And here, since we've done everything that we need to do, we will now come back and write this in terms of sine now. So we have 5 sine of theta minus 2 times sine of theta plus 3. So that's our first example for this type. So now let's go here to the second example. Okay. For this particular example, we're going to use factor by grouping to help us out here. So we're going to group the first 2 terms together, second 2 terms. So if we look here, I'm going to rewrite everything in terms of s now. So this is going to be 16s cubed minus 12s squared grouped plus 36s minus 27. And so here we see that we have common factor of 4s squared here, because of course this could be written as 4 times 4s squared times s for the first term. This could be 4 times 3s squared for the second term. And if we look here, we see that we have a common factor of 9, because 9 times 4 is 36, 9 times 3 is 27. So we'll have 9 times 4s minus 9 times 3. And so we have the 4s squared here, 4s squared there. So we factor that out, and we just have a 4s left first term, and we have 3 left in the last. We factor out the 9 in the second group. We have 4s in the first term, and we have 3 in the second. And of course, that needs to match. And it does, so we factor that out of each term, and now we end up with the following. So if we continue on here, if we write everything in terms of sine again, go ahead and move this up. If we write this in terms of sine again, then we end up having 4 sine of x minus 3 times 4 sine squared x plus 9. And so again, we will not be able to factor out this last factor here, because this is the sum of 2 perfect squares instead of the difference. All right, moving on to the last example on this page. So now we're dealing with tangent. So we're going to let t be the same thing as tangent of y. And of course, if we do that, then this will be t squared plus t minus 12. And so if we take it from here, we'll go ahead and factor, have a plus or minus there, t. And so we need factors of 12 that give us a difference of 1. Of course, 3 times 4 sort of fits that. And since we need the 1 to be positive here, then we're going to put a 4 there and the 3 there. And of course, if we multiply that out, we'll see that minus 3t plus 4t gives us a positive 1t, which is what we need. So therefore, if we write this out, this will now be tangent of y plus 4 times tangent of y minus 3. And so we'll move on to the next examples. So for this example, we are asked to use trigonometric identities to write tangent in terms of sine. So we'll go ahead and do that. So if we take tangent, we know that tangent of x is going to be the same as sine x divided by cosine x. Okay? And so looking at cosine x, if we're going to write this in terms of sine, what we know is that sine squared plus cosine squared equals 1. So if we subtract sine squared from both sides of this particular identity, then we end up having cosine squared is equal to 1 minus sine squared. And of course, if we do the principal root here, that would be plus or minus square root of 1 minus sine squared. So we could come and rewrite this as sine of x divided by plus or minus square root of 1 minus sine squared x. And of course, the plus or minus part would depend upon the value of x, in other words, the angle x and what quadrant that it's in. Since we're dealing with the sine function, if we recall our quadrants, we know that points look like this in these quadrants. And here we know that this represents x, that represents y, and in terms of trig functions, we know x would be the same as cosine of an angle, and we know y is the same thing as sine of an angle. So here we see that this sign would end up being positive here for all the quadrants where sine is positive. So sine is positive in quadrant 1 and in quadrant 2. And so sine would be negative here in quadrants 3 and in quadrant 4. So depending on what value of the angle it would be, that would tell you whether you would use the positive or the negative sign there. All right, so let's go ahead and move on to the last example in this particular video. And so this question asks us, it says, it's given us that sine of x is going to be a negative 1/3, and the angle is going to be in quadrant 4. And what we want to do is compute cosine x and cotangent x, okay? So what I'll do here is, since this is a little more, I'll go ahead and zoom out some so that we can see the entire problem, okay? So now that we have this, we'll start off with what cosine is. What sine is. So we know that sine of x is equal to a negative 1/3. So if we were to square this, of course, this would give us a positive 1/9. And so from our identities that we know, sine squared plus cosine squared equals 1, we would also know here that if we wanted to do cosine squared, this would be the same as 1 minus sine squared. And so we know that sine squared is a positive 1/9. So 1 minus 1/9 is going to give us 8/9. So this means that cosine is going to be plus or minus square root of 8 over 9, which would be plus or minus square root of 8 over square root of 9. And if we work this out, we know that square root of 8 is the same as 2 square root of 2, and square root of 9 is 3. So now we need to decide whether we're going to use the plus or the minus. Now, how we decide that is to think about what sine represents. So sine is representing the y coordinate. So since we're saying that our angle x is in the fourth quadrant, we know that points in the fourth quadrant look like this, x, y. And so since sine is negative in that particular quadrant, we know cosine, because we know x represents cosine, y represents sine, cosine is positive. So we end up using just the positive version of this. Okay? So now that we know that, we can go ahead and figure out what cosine of theta is as well as cotangent of theta. So therefore, cosine, of course, we've already figured out that answer, is 2 square root of 2 divided by 3. We'll go ahead and write that there. And then cotangent of x is going to be the same as cosine of x divided by sine of x, or the reciprocal of tangent. And of course, cosine is 2 square root of 2 divided by 3, and sine is a negative 1/3. So when we go and work this all out, we'll do a keep change flip. That reduces to 1. And so our final answer here ends up being negative 2 times square root of 2. So cosine x is 2 root 2 divided by 3, and cotangent x is negative 2 times square root of 2. Now, we could have also done this same problem by drawing right triangles or whatnot, but now that we know the identities, we don't necessarily have to do that. We only need to pay attention to what particular quadrant the angle is in, and that sort of helps us out there. So this concludes the lesson on this particular video.